Describing color is chapter 2 in your book. What we're looking at is describing color in different ways so that we can talk to people about it. Color is a perception, but we have to put it into some kind of form so that we can communicate with other people so that we can decide what we want to do. So there's different types of systems that are talked about in your book. So when we talk about color, to start with, it's a pretty complex issue and can be described several different ways. We can use physical properties. We can talk about color in terms of concentration of colorants, concentration of dyes or pigments. We can talk about it in terms of the light source spectral properties. Light source spectral properties, so that's what we were doing before. We said that light is made up of different wavelengths, and if we break those wavelengths apart, we have different colors. So for instance, color of wavelength 550 nanometers is a green light. See that light, we perceive it as green. We can also talk about color as physiological properties, so how our receptors in our eyes respond to that, turn it into opponent signals, and send it to our brain. Or we can just use names to describe it. We can say red or pink or blue or green, and use attributes for color that are hue, chroma, and lightness. I think we talked about those a little bit. Ways of describing color. Over the years, developed many systems throughout history to describe these ways of looking at color. Some of them are thousands of years old. Artists have been drawing things for thousands of years. They go back to the old cave drawings of artists, and they needed colors to represent what they saw in nature, so the colors that they made up were natural. So our color systems can be divided into several types, and they are either theoretical, based on just theory, based on actual sets of samples. You're familiar with that. Go to the paint store, for instance, something like that. You see sets of color samples. And they could be based on physical measurements and computation. As we move deeper and deeper into describing color and working with color, that's the way we're going to be leaning. We need a system that's very precise in how we describe colors. Really separate colors. You'll see that if we just use words, we can't get it precise enough to know what we're really talking about. If I say blue, for instance, we need to be more precise. The text describes three types of systems. Color mixing, governed by color physics. Color perception, governed by visual experimentation, where people did experiments to see how they perceive colors, and did it over a large group of people so that you average. Everybody's a little bit different, so there's no one person that has perfect color perception. Everybody's a little bit different. So they do these tests, these experiments with a fair amount of people, and then they average it. And there's also color matching that is also governed by visual experimentation, but different kind of experimentation. You're actually matching something. So there are several different ways of developing these systems. Some of them are better than others. Some are more complicated, are fairly simple. So first thing is systems based on color mixing, and that exemplifies the relationships between color primaries and their intermixtures. So you have a certain set of colors that are your primary colors, and then all the other colors in your gamut or your palette are made from those usually fairly small amount of colors. In printing inks, the colors that we use, and we talked a little bit about this earlier in the class, we use cyan, magenta, yellow, and black. So with just those four colors, all the colors that you see in printing, say magazines, that's what they come from. They don't use a bunch of other colors. They just use those colors, and by intermixing them, you get the large number of colors that you see. CRTs are becoming more and more important. I mean, everybody has computers just about these days, constantly looking at computers. So they have phosphors of red, green, and blue, similar to what we saw in TV screens we mentioned before. And we're also paint systems. Go to the hardware store and you want a certain color, you go look through all the swatches and everything, and you come up with the color that you want. Or more likely for the men in the audience, your wife comes up with the color that you want, or that she wants. If you look on the shelf for that color, you don't really find it. They don't have all those colors that are possible in all the examples that they have on the cards, because that would be a huge amount of inventory. What they do is, once you tell them the color you want, they go to their paint mixing system that has several highly very chromatic colorants in it, and black, and usually they start with a white base and they put in the ingredients to make the color that you would like. Depending on where you get your paint and how well of a mixing system they have, the color that you bought will look something like the color that you expected it to be. Sometimes it's pretty close, sometimes it's not so close. That's one of the things when we talk about color matching and working with color, is a system that's repeatable. If you have a color that you're looking at, you want to be able to reproduce that for your customer. Some systems work pretty well at that. Some are a little more suspect. Sometimes you take the paint home and put it on the wall and say, that's the color I thought it was going to be. If you and I did that, we'd say, oh, that's close enough and that's good. But your wife would look at that and say, I don't like that. We talked about metamerism there. If you change the ingredients, that changes what the colors are and maybe metameric. So you could actually, if you bought your paint, 2 years ago and painted your room, and you had maybe a big hole in the wall and you didn't have any extra paint, and you wanted to go back and get some more paint, and you had it mixed up again, and you brought it back, it may not match anymore. Or it could match under, say, you paint it at night when you have the light on, and it matches, and then the next day in the sunlight, you look at it, and now it's different, and it doesn't match anymore. So all those things are possible. Generally speaking, they don't change the pigments that are in their mixture, but they could change suppliers, and that could be enough to throw that off. Every day in industry, the accountants are always looking for cheaper suppliers. Salespeople for those suppliers may say it's exactly the same, but it's not always. When we talk about colorants and pigments, we'll see there are some general, generic kind of colorants, but each manufacturer's pigment of the same type may be different, and there's lots of reasons for that to be different. The term here, are primary, one of a set of colorants used in a coloration system. That's the term we use for primary. And a color gamut is the range of colors produced by that system by those particular primaries. And generally speaking, there's only a small handful of primaries. You don't have 20 primaries. You usually have 3 or 4, 5 maybe. The idea is to keep it as simple as possible, but make as many colors, because what you're trying to maximize is this color gamut. How many different colors can you make with your system? Because that makes it the most flexible. Everybody's happy with the colors you can make. So some examples of systems based on color mixing. I mentioned printing, cathode ray or CRT displays, color TVs, paint dispensing systems. Those are all things we mentioned and we're familiar with. And usually there are 3 primaries that these systems are based on. And here's an example of a system here, color CRT display, where we have red, green, and blue phosphors. You may have to stretch a little bit looking up on the screen there that they're actually red, green, and blue. But if you look in your book, see, that's why you spend the, $120 on your book, is so that you have the true colors. Just imagine that's red, green, and that's what's in your TV or your CRT. There's energy source, the electron gun behind it that can excite the dots as a group. The 3 of them kind of work together as a group. Depending on how much energy hits each one of those dots, that's how much of that phosphor is excited, and you can think of how much percentage of the total color comes from each one of those 3 colors. And they add together, and then you see the color that is wanted. If you look real close on your TV screen, there's little dots there. Nowadays, there are a lot more dots than there used to be. Back in the old days, you could go up to the TV and you could actually see the individual dots. Now, with with the, you can even see, if you look on that one, you can see the lines going across that. It does. The more dots, the more sharper the picture is. So, you know, when you go out and you buy your high-def TV with the 1092 lines one direction, and I forget what it is the other direction, that's much more sharper of a picture than back when they used to have 500 lines. Back in the dark ages when TV didn't run your life. A computer graphics color, this is a field that has really grown in the last few years, is how do you get the color right on a CRT screen? Because so much now is done by computer. Think of how much shopping is done now on the internet. People want to know what they're going to buy is going to look like, especially the color, before they buy it. So if your screen is not true, or like that last slide I showed you with the red, green, and blue, the color's not going to be right. You buy it, get it home, and say, geez, that's not quite what I wanted. There's a lot of work that's being done to make computer screens more accurate. And if you get into color business, and we went on a tour of A. Schulman down in Sharon Center, they have some special CRTs that are calibrated often so that they show the true color. They claim to show the true color. They're better than they ever used to be, I'm sure, but I don't know if you could say it's always right. There's a lot of different things that can happen. This is a little bit different than we described in Chapter 1. We have hue, lightness, and saturation versus, I think we called it hue, lightness, and chroma. So we can have a RGB color cube. The next slide will show the relationship of the colors red, green, blue, white, and black in three-dimensional space. And we call this, a depiction like this, a color space. When we talk about color gambit, we talk about the color space. And it shows where all the colors are in relation to each other in 3 dimensions. Whenever we talk about color and want to describe the system or where all the colors are, we have to use 3 dimensions because there's 3 attributes that we have to describe. We can't just do it with 2 dimensions. It has to be a 3-dimensional type model. Here's a picture of that sort of thing. You can see where the different colors are in relationship with each other. In a little bit, we'll talk about the Munsell system, or actually have a model. Another way of looking at how the colors are related, and that's kind of typical to what we'll see in other models where lightness and darkness kind of top and bottom. And if we go around in the circle, we have the different hues. Generally speaking, if we are in the center of that structure, it's grays, dull colors, not very chromatic. The farther out we get from the center, the more chromatic the color is, the deeper, brighter, vivid, whatever term you want to use. There's a lot of terms that are kind of used interchangeably. You can have colored light mixing systems. Unfortunately, we don't have this anymore, but at one time we had a spinning disc system that was pretty interesting how it worked. It was almost worked like mixing paints, but there was no liquid involved with it. There were several high chromatic colors. There was red, green, blue. I think it had a purple in it, black, and white. So they had basically shiny paper painted or printed with these colors. And then what would happen is there was a disc, a round disc that would spin. And you could expose whatever amount of each one of those colors you wanted. A picture of it looked like this. Say you had this much of it was white, maybe a little bit of black, and say a blue and red. So that's what the disc would look like when it was standing still. And you could see the individual colors and what kind of percentage of each one of them, kind of like a pie chart. Think of it as a pie chart. But then you turn the motor on and it spun. And when it's spun at a couple thousand RPM. And what you would see on this disc is one single color that was the same effect as if you mixed those colors if they were, say, the chromatic colors in a paint system. And you would see only the single color because your eye can't see each individual one. It acts as a mixture, and you can get a color with it. The idea was if you had one and your customer had one, you could dial in each one of those colors and you could have numbers that described it, and you could look at your disk and say, yep, that's the color I want, and tell your supplier that's the percentages I want, so make that color for me. Never really caught on, but it was kind of an interesting system where when it was stationary, it looked like that. When it turned, it looked like a single color. And that's called the Ostwald system. There's also something called a color harmony manual, and if you go through your book, they describe these different systems a little more detail. We don't generally use all of them in industry, so I'm not going to talk specifically about them, but you can read those. Color printing systems, there's something called the True Color Process Guide that has more than 18 colors in it, and you can pick what colors you want. For instance, in printing, it's made up of, again, some primaries. Focal tone color system is less than 1,000 colors, so it's less flexible, doesn't have as many, but it's still a lot of colors, 1,000 colors. Probably the most famous and the most used system is called the Pantone system, and it's based on 14 basic inks. So these are all ink systems. There's also a True Match for CRTs. The Pantone system actually has a plastic system also that can go along with it. Sometimes even in plastics, customers will use the Pantone system because it's so widely used. It's a book that has, it looks sort of like what you see at the paint store with the different colors on them, and you can spread it out and see all the different colors. It gives the formulas for that too. And what suppliers do sometimes is they'll look at their Pantone book and say, I would like this particular color in the Pantone book, give you the number and say match that. The problem is if you have to match it in plastics is you generally can't use the same colorants in plastics that were used in that ink system. So if you can't use the same colorants, what's the problem that can occur? We talked about it a little bit earlier. Two colors match under one. Metamerism. If you have to use different colorants, there's a very good chance that you're going to have a metameric match. And you definitely won't be able to use the same colorants that are used in the Pantone ink system if you're going to be making plastic parts, especially if they're high temperature resins. So you have to be careful with any of these systems if you try to match them in plastic. So some pictures here. Here's an example of what Pantone or True Color cards look like. You can see the two of them. This came out of your book, but they have numbers that go along with them. For instance, Pantone 2000 CV. And if you looked it up, somebody else could have a book, they could look it up, and you'd both be looking at the same color. The hope is that both of your books actually look the same. One of the largest problems in industry and matching colors is that the customer wants a certain color and has a target for that. And then somehow he has to communicate that to the color supplier. And if that isn't done properly, the color supplier may have a different color that he's matching than what the customer actually wants. You might think, well, that's pretty basic stuff, but it does happen. So it's important that the standard that they want is the same standard that you're matching. And some care must be taken to do that. But that just shows you an example of what those look like. Those are in your book. Paint cards. The paint industry uses color cards for communication. Each sample has a specific formula. So once you pick out the certain color, misty green, or that's the thing about colors that you get for paints. They all have these names that mean absolutely nothing. We'll talk about that in a little bit. They have a number formula that goes along with it for how much of each pigment goes in there. You may have had experience paint not matching the sample card. Again, that is on a piece of paper, so the medium is different than when you put it in your room. And you're also looking at a little piece of color versus your whole wall. So that can affect it. And the different colors in your room, different light sources, all that can affect how the two different colors look. It's supposed to be the same, but they may not end up exactly being the same. So there's an example of some Sherwin-Williams there, paint colors. And then there's systems based on color mixing. And here, I kind of mentioned some of these already. The critical issues for color specification. First one is, if every aspect of producing visual examples is not highly consistent and standardized, large variation in perceived color can result from identical specifications. So if the batch of color that is made up either for the primaries or for the mixtures is not done very accurately, it's not going to match. And if it doesn't match, then that's not a good thing. Excellent consistency is extremely difficult to achieve in printing systems because of the variability of the process. Even though you try to control everything as tightly as you can, variations always occur. In industry, there's always variation in any kind of process. The hope is that it's very small and unnoticeable, but color is very, very touchy, very critical. So you have to be extremely diligent in what you do and reduce the variability. But sometimes there's just natural variability that you can't 100% get rid of. Some other issues, primary amounts define the specification, not the resulting color. So when you make up a color, you're working towards the formula, and you get the formula just right. But that doesn't necessarily mean the resulting color will be exactly what you want. Problems with using ink recipes for specification and other materials like plastics. Printing systems have poor consistency, causing samples not to be consistent, which is a problem. And we mentioned before, metamerism is possible and most likely probable if you can't use the same colorants in your plastic as you can in the ink. And even just being in plastic, because it's a different material, can cause metamerism, even if you could use the exact same colorant.